Bismillah ar-Rahman ar-Rahim. Today we will be discussing breathing and scavenging systems. First of all, the open system is characterized that there is no tubing or valves or reservoir bag. We can see from the figure, figure 8, an anesthetist is approximating a tube on the face of the patient. Of course, most pediatrician use this system during resuscitation of a baby, and this reminds us with Schimmelbusch mask, which was used before. The second figure shows the what we call the Edinburgh mask, which has a wide opening. This, of course, minimizes the dead space. The third one, where we introduce a cannular near to the mouth of the patient by a special gag into the mouth of the patient. The advantage of open system is there is no resistance to the patient breathing, but the disadvantage are there is difficulty to control the concentration of oxygen and other gases. And during the peak inspiration, what's the meaning of it? It means that sometimes the patient is in need of taking around 50 liters per minute. You see, so he will gain such an amount from the surroundings, so we will lose control on the concentration of the gases administered to the patient at that time. Of course, we can support the as a solution a Venturi mask to increase the flow to give what we call the peak inspiratory required flow. The second point is the non-rebreathing valve system. The most famous one is the Ambu-E valve, which is made of a molded rubber one-way inspiratory and expiratory valves to allow the patient to draw gas. And then we have a reservoir bag, as we can see, supplying whatever gas to the patient, equaling his tidal volume. This is present in what we call the QuantiFlex machine, which is being used by the dental physicians. It can be used for controlled ventilation. Meanwhile, you can use it as a non-rebreathing and a controlled ventilation as long as the two valves are present. And this is the figure showing how the valves are being working during inspiration, expiration. On the other hand, we have what we call the Ambu E2 valve. This valve is used only on resuscitation, where we omit the expiratory valve. You see, sometimes we find resistance. We know that the resistance of the expiratory normal and expiratory valve that is present the circuits around 50 Pascal, but sometimes the resistance can reach 100 to 200 Pascal, which is uncomfortable for patients. Of course, airmen and firemen. Airmen means the pilots use such system, so that we have to have a special type of valves with minimal resistance. The tri-surface apparatus, as we can see, it is a portable and a very light draw-over apparatus. Uses what we call the silicon Lerder valve. It's made of silicon, and this is the figure showing it. How does it work during operation? It is a type of Oxford miniature vaporizer. The T system, which is known that as Ayer T-piece. It was invented by Dr. Philip Ayer 1937. It has no valve, and it is a simple method where the fresh gas flow supplied ought to be twice to twice and a half of the normal minute ventilation to minimize the rebreathing. And the diameter of the tubing ought to be not less than 22 millimeter mercury. This is the figure we mentioned several times before. so that this system, the expiratory limb ought to have a volume not less than the tidal volume of the patient. I will show you later on how does it work in a figure. This is the figure we can see in front of us of an expiratory limb of the T-piece, where we have A and B and C and D. A represent the first thing of expiration, which is the tidal volume, and then we have after that in BC the mixture of alveolar and tidal volume, and lastly the D area, where we have mostly the fresh gas flow coming from upward tube by 4 liter per minute. So if we have enough expiratory pause, most of this expiration will be expelled before and no dilution of the inspiratory gas will occur. But if we have no pause, the patient may take some of his flow from this area of D, where it contains some sort of the expiratory valve, especially in peak flow. So sometimes whenever we need an extra flow and there is no enough minute volume, the patient may withdraw this peak flow from outside the breathing system and causing rebreathing. This figure shows what is the optimum timing for us to minimize the minute volume. So if we have enough time at the end expiratory pause of 1 second, the required minute volume can be 8.5 liter per minute instead of 14 liter per minute if we don't have a pause. So this figure, I will show it later on, represent the tidal volume and the stages of inspiration in seconds. And this is the process of inspiration, expiration, and these are the two minute volume rate, as you can see, showing that whenever we have a pause, there is enough time for all the expiration to be expelled, so that the patient will not rebreathe the previous expiration. So this is the advantages of the T-piece. It's used particularly in pediatric, but it can be used in adults. But we ought to use to a much tidal volume. As we said before, the minute volume is twice to twice and a half of the normal minute volume of the patient. Of course, whenever we have a large minute volume, it represents a resistance during expiration. You see, you must put in your mind this point. And of course, we have the problem of pollution due to the expel of the gas outside the system. The coaxial T-piece, as you can see, this is the T-piece as we mentioned before, and the coaxial means two tubes inside of each other. It makes it compact, you see. So this is the system which we call it the Bain system in the United States, and pendulum coaxial system in Britain. You see, so we have an inner tube. This inner tube ought to be in position. Otherwise, if it's broken, it will increase definitely the lead space. The second system is the McGill system, which was introduced by Ivan McGill in 1920. It's made of a bag and a fresh gas flow and expiratory valve. What happens during the process of expiration? First of all, as we said before, the tidal volume is being released, and then we have a mixture of the tidal and the alveolar ventilation. And at a time during the peak expiration, this bag this reservoir bag, this is an adjustable pressure bag, is increased in pressure. So whenever it increases in pressure, it increases the circuit in this area, opening the valve, so that what will be removed at this area will be the alveolar gas, and then this bypassed or what we can consider the tidal volume, which had bypassed this area, contains the tidal volume. So we have a part of the expiration, which is the tidal volume, where we have less CO2 and more CO2 oxygen will be present, so that whenever the patient is required to have less than his own tidal volume, he can take this from this remaining tidal volume present in the expiratory limb when all the alveolar gas has been expelled from the expiratory valve. So this is the advantage of the McGill, that we can use less than the normal tidal volume during the McGill system. We can use almost 70%. I forgot to tell you that the T-piece during spontaneous ventilation needs around from 2 to 2.5 times the normal minute ventilation. So whenever I mention a circuit, you must put in your mind whether it's being used spontaneously or for controlled ventilation, how much is the minute volume used, and what are the advantages and disadvantages of it, you see. Of course, whenever I tighten the expiratory valve to use it as for controlled ventilation, this situation which we had mentioned before, where the alveolar gas has been expelled, will be completely changed, and the constituents of the gas in this expiratory limb will be changed, so that it will not give us a proper mode of ventilation, where there will be some sort of rebreathing. This is why we ought to use this system for controlled ventilation for only a short period. Sometimes this valve, of course, is nearby to the patient, be heavy. So sometimes we make it remote from the patient, as you can see from this figure. And we can use, of course, sterilizing circuits and removing it after the accomplishing of the surgery, maintaining the expiratory valve. So this is a situation where the McGill expiratory valve could be removed from the patient. The coaxial McGill system, as you can see from the figure, in comparison to the paint circuits, we have the expiratory tube instead of the inner tube. Yeah, this expiration has been connected to the expiratory valve, and the inspiration is being controlled by the outer part. So the patient inspires through two areas. So to minimize the resistance, this area ought to be larger than that we have seen in the pain circuit. The closed circuit, of course, we'll show it later on. As we know, it minimizes the cost of the inhalation anesthetics and minimize the amount of oxygen consumption. And of course, it preserves the humidity of the expiration of the patient. And we ought to know that we have what we call the 4 to 8 mesh, which is the proper size of the particles of the canister, the soda lime. What's the meaning of that? It ought to be, if we have strands made of an inch strand, and we are dividing it into 8 or 4 squares by vertical and transverse strands, it ought to only transfer the size of 4. You see, not the size of 8, to assure a proper surface area for absorption and to minimize the resistance. So whenever I say what's the meaning of 4 to 8 mesh, that means that we have a mesh where will only of 1 inch will only, if we divide it into 4 or 8 by 4 or 8 strands, it all will permit the size of this particle. So it will have less resistance and more efficiency in absorb. This is why we call 4 to 8 inch. It can be used as a question, of course, during controlled ventilation. Of course, we can use the circuit outside or inside the circuit, and we have to have an accurate system to measure all this flow to minimize the drawbacks. Of course, the advantage of it, of course, it uses, as we said, less amount of anesthesia and oxygen, and minimize, of course, the humidity. But the disadvantage is a complicated system made of many parts which may be dislodged and causing leak, and it's difficult to be sterilized. Sometimes, of course, we ought to make it not completely closed system, but make it semi-closed, so that we can first of all, at the beginning of anesthesia, get rid of nitrogen, which is present in the circuit, and then close it to be a completely closed circuit. Of course, the semi-closed increases the incidence of pollution. An alternative classification of system is Mapleson. Mapleson, we have A, B, C, D, E. We can omit the B and the C, and with the Mapleson A, of course, is, as we can see, is the McGill circuit. The D circuit is the Payne circuit, and then we have after that the Iris TBs as E system, and then whenever I apply a reservoir bag to the Iris TBs, we get what we call the F system. So this is a classification, and sometimes there is a confusion between the United States and Britain regarding whether it is a semi-open, semi-closed. So we will not discuss the difference between both, and we consider the system we had mentioned before as a classification, and Mapleson as another classification. The resistance of breathing, of course, we must put in our mind whenever we have a circuit. As a general, we ought to have a proper diameters. We ought to minimize the resistance by the valves, using light valves instead of the high bring valves. We ought to have a system to satisfy the patient regarding the peak inspiratory flow. All these are methods to satisfy the circuit. So each circuit, as we mentioned before, has its advantages and disadvantages. Of course, the open system, as we mentioned, there is no valves, there is no reservoir bag. All these are methods to minimize the resistance. And as we know, the 22 millimeter tubing is important. Sometimes we use 30 millimeter to minimize the resistance. Whenever the patient is spontaneously breathing in such system, he may be uncomfortable. So we use a large systems, as we had said, 30. Sometimes, of course, as we said, the valves ought to be minimizing the resistance, which is 50 Pascal. Whenever it reaches 10 to 50 Pascal, it will be nuisance to the patient. So we ought to have special types of valve. All these are methods to minimize the resisting of the breathing system. This figure shows the patient inspiring 0.4 liter of gas, and we can measure the resistance of the breathing during inspiration or expiration. Figure A represents the simplest T piece without a bag. B represents the non-rebreathing or circle. The C represents the McGill circuit, and D represents the T piece with a reservoir bag. You can see the line consider the separation between inspiration and expiration. We call it 0. So this is the zero. We can see that the loop is being shifted upwards, and this is much shifted upwards. So this is the difference between the four system we had mentioned before regarding the resistance of breathing. The work of breathing, as I said before, of course, the work of breathing is estimated by multiplying the pressure by the volume. You see the pressure required to the volume induced. So when we mentioned that in the work and power chapter, I remember that we multiplied 0.6 times 0.6, the 0.6 Pascal time 0.6 liter to reach 0.3 as a estimation of the work of breathing. So the system adds more work of breathing. As we can see that the work of breathing is around 27% increase in the work of the breathing of the patient if he is not breathing through a circuit. So the circuit increases definitely the work of breathing, as we can know that the work was 80 millijoule. Safety of the system, breathing system, of course, we ought to have a correct assembly. There is some sort of matching between the components. We have to have a screw collars. Sometimes you do a taper gauge. This measures the dimensions of the connecting tubes system to assure that they are well fitted, and we must put in our consideration that the valves must be cleaned from the water vapor, otherwise they will stick and increase the pressure. The scavenging system, which is taking the exhaust outside, can obstruct and affect the airway of the patient, inducing a pressure. Of course, the advantage of course of this inflatable bag we have in the system. Whenever I apply the Laplace law that pressure equals to T on R, this the advantages of the elasticity of the bag. So the bag can be much increased in diameter, yet the pressure is being preserved. You see, so if this bag is not elastic enough, it will be a problem, which will increase the much pressure in the anesthetic circuit. The bag induces around 4 kilopascal pressure, you see. Of course, we must put in our point that the inner tube of the coaxial tube, if it is being detached, it will increase the tidal volume of the patient. And the expiratory valve of the patient, whenever it's nearby the patient in the McGill system, definitely it decreases the tidal volume. I'm sorry, the dead space. So if this, as we said before, the bag loses its elasticity, the pressure may increase up to 35 kilopascal per second, which will may affect the parts of the machine. This is I don't want to go much about ventilators. We are representing the pulmoventive ventilator, where we have a tidal volume of 7 liters per minute is being administered through a pillows, and this pillows is controlled by, as we say, as we can see, springs. And this, whenever this pillows is being inflated to a certain point, this system has a lever. This lever looks like that what we had in the domestic home flow meter. It opens the valve, releasing this volume to the patient. Of course, it's been adjusted so that it will not reach the full pressure, which was 10 to 12 kilopascal to the patient. We can control all this by special valves. So this type of ventilator, it's volume cycle, because it cycles after a special volume, and it is it doesn't have a really constant pressure during inspiration. It's variable. So whenever I want to classify this type of ventilator, it's difficult to state its real classification. And of course, if I open the system to the atmosphere and making it used for spontaneous ventilation, we can consider it as a TP's system. The scavenging system, of course, it can be spontaneous by the patient's expiration to be exhausted outside the room, or it can be active by a pump or a fan. We'll show some figures later on instead of talking much about the system. Of course, as we saw, it can be passive or active. And the active has a components. These components are made of 3 parts, as you can see from the figure. We have a disposable port, and then we have a receiving system, as we can see, and we have a cylinder, and then we have a disposable system. This disposable system is made of a fan or a pump to remove the exhaust of the inhalation anesthetic outside the system. Of course, as we can see, the tubing has to have around 30 millimeter diameter, and there is a male and a female connection to assure that there is no dislodgement. And this system reservoir is a cylinder which has an air leak, so it will not reflect back to the patient either positively or causing negative pressure on the patient. And this after that goes to a special pump or a fan system to go outside to the patient. So we have what we call the 3 active parts representing the active scavenging. See, this is the method where we use a tubing system on the mask of the patient to remove the exhaust of the patient. And we have of course, we ought to have a special flow. This flow, of course, has a special rate to minimize the resistance and to assure that this flow is being properly dismissed from the apartment. And we have here, this is the part showing the Venturi system to induce the flow, increasing the flow. You see, this is the expiratory valve, this is the bag. I'm sorry, this is the mask and the bag. All these are systems to assure that the system has a proper flow without any much resistance. And this is simple method where we can just suck what is present above the expiratory valve by a funnel, as you can see. It ought to be close by to the patient, of course, and it ought to have a special proper flow to minimize the pollution. Of course, this funnel can be reversed downwards the opening of the T-tube. You see, you can use it to collect instead of putting the funnel in the proper situation to remove what is present. This is the Leerder. I'm sorry, is the ambu valve, as we can see. During inspiration and expiration, it can be, as we said before, used as a non-rebreathing or a controlled ventilation. And this is the T-piece, and this is the expiratory floor, and this is the D area where whenever they have a proper expiratory pause, we can remove all what's present here, and only this area will contain the fresh gas flow. You see, if this expiratory tube is omitted, this is the problem, and the patient is in need of peak expiratory flow, as we said before, 50 liter per minute, he will gain this from outside. So this is important of the expiratory tube, where he can find his amount required. And this is the McGill circuit, where the pressure of the of the circuit by the bag is capable to open the valve, which is 50 Pascal. All these figures you ought to remember. At that time, of course, the alveolar gas will be dismissed, and this expiratory tube will only contain this space where there is enough oxygen and less CO2 to be rebreathed to the patient, minimizing his requirement. And of course, this is the remote valve of the McGill circuit. Whenever I want to make it away from the patient, suppose the surgeon, we are disrupting the patients, the surgeon, so we can use this. And then when we have a situation of contamination, or we want to minimize the cross infection, we can remove this part, and then we can of course sterilize this area. For the thing that I missed, that sometimes to assure that the system has a proper assembly, these valves may be damaged by, if they are plastic, by sterilization. And this is the LAC system, where the expiration is the inner ward, and of course is the closed system, where we have the 4-8 mesh system and the expiratory valve. And this is the RSTBs, as we can see, and the pain circuit. And this is the resistance during expiration. Whenever I inspire for 0.4 liter, and I measure the resistance, and I can measure the work of respiration, different types of circuits, as we can see. And this is the zero line representing inspiration, expiration. So all this shows the resistance, whether it's in the during the period of inspiration or the period of expiration. It is a tough subject. I hope that I succeed. I'm sorry for my mistakes. Wassalamu alaikum wa rahmatullah wa barakatuh. See you later, inshallah.